to the second and final part of this two-part series on percentages. Now, in the first tutorial, I just introduced the concept of the percentage as 1/100th, and we just looked at some very simple examples. Here, I want to deal with two slightly more advanced topics. One is the accumulation of percentage increases or decreases, often called in financial terms compound interest. And then I'll talk about a difficult topic called reverse percentages, which I think everyone finds a little bit mind-bending and tricky. So let's do this accumulation first. So let's take an example, best done with an example of a bank account. And let's go back to that individual that had £100 in their account, and the interest rate per annum, so each year the interest is 5%. And let's see what happens after, let's say, 3 years. Well, we've already done the calculation for year 1. So in year 1, we worked out 5% of £100, and we found that to be £5. So the new value is £105. Now in year 2, we have to work out the interest on £105. We don't apply the 5% a second time to the original value of £100. The new value after 1 year in the account is £105, and we're going to take 5% of that new value to work out the interest earned in year 2. Now this, unfortunately, is where I have to get my calculator. Just arithmetic on paper is not so good when you come to these type of percentage problems. So I'm going to work out 5% of £105. Maybe I can actually show my calculator here. You'll see it's a steam-powered calculator from the Victorian times. Now the way that I will do this is to write 5% as 0.05, and I'm going to multiply that by 105, and I get 5.25. Okay, so that's £5.25. And so the new value in the account is £105 plus this £5.25. And so that will be £110.25. And then in year 3, we have to work out 5% of that. So again, in full glory here, 0.05 times 110.25 is 551. It's quite modest, isn't it, the increase? So 5, I'll just round up there. And so the new value after the 3rd year is this plus 110.25 is £115.76. Now the point of this really is that one doesn't want to do these calculations year on year. There's a much faster way of doing this. If you're given a percentage and you're asked to calculate the accumulation after a certain number of years or iterations, the way to do it is the following. You take the original value, which in our case was £100, and then what we've effectively done for year 1 is multiply this by 1 plus 0.05. This is the original value, and this is the percentage increase. And we've essentially continue to do this on each successive year, effectively multiplying these amounts by 1 plus 0.05. And we want to take this number, therefore, to the power of 3 for 3 years. This will give us the accumulated value after 3 years. So let's work that out. I have 1 plus 0.05. I raise that to the power of 3, and then I multiply by 100, and I get my value, £115.76. You see how much simpler that is than going year by year. Let's just do another example to quickly show you this. So let's imagine that we have a car that was bought new at a cost of, say, £15,000. Okay, and let's say it depreciates. The value depreciates by, let's say, 8% a year. We often write PA, per annum, for per year. Let's say the value of the car after, let's say, 7 years. Okay, so we're just going to do this right, cutting to the chase with the fast method. We take the original value, which is 15,000. We're going to multiply by 1, which gives us the value, take away 8%, and 8% is 8/100ths, or in other words 0.08. So after 1 year this would be the value of the car, but we want to know after 7 years, so we're repeating a multiplication of this factor 7 times. And so the way we can represent that is by just raising this factor to the power of 7. So let me just do that then. I have 1 take away 0.08. I'm going to raise that to the power of 7, and I'm going to multiply it by the original value of the car, 15,000, and I get 8,300, and I'm just going to round up there to the nearest pound, £8,368. Okay, so that's how you go about calculating sort of a compound interest or an accumulated deficit year on year. You're typically given 2 pieces of data, a percentage change, either an increase or a decrease. It's crucial to know whether you are increasing value or decreasing value, and then you're given a number of years or a number of iterations. And then you can just take the original value and then you multiply by 1 plus or minus, depending whether it's an increase or a decrease, the percentage, and then that whole number raised to the number of years or iterations. I keep saying iterations because this is not always about money. Let's just do one more example. Let's say you have the population of the Earth. Okay, I'm just going to make this up now. In fact, because I don't know the numbers that well, let me have an imaginary planet. Let's say the population of Mars sometime in the past is 1 million. And let's say that let's be optimistic, let's say their population increases by 10% every century. Okay, so in this case it's a century that is the unit of time, not 1 year, and we want to know the new population after 1,000 years. Okay, so it's going to be 1 million multiplied by 1 representing the original value plus 10%, which would be 0.1, and then this applied for 10 centuries because it increases by 10% every century, and after 1,000 years that's 10 centuries. So we raise this to the power of 10, and let's see what we would get. I'm actually going to do this in units of a million, so I'm just going to write a million as one lot of a million. This is 1.1 raised to the power of 10, and it's 2.59 million. So that 10% increase every century after 10 centuries would more than double the population of Mars. Right, okay. Finally then, let's turn to reverse percentages, and we'll just do 2 examples of this. This is a topic, I just don't know, it creates such confusion. I've seen lots of different ways of going about these problems. I'm sure they work for some people. I will show you the method that I use, which might seem, I don't know, a little abstract possibly, but I think it is the clearest in fact. And this is best done with examples. So let's say that someone has received a bank statement and they are told that their balance in their bank account is, just make up some number, £420, and let's say that this is after having received 8% interest that year. So this might be some super earning savings account, something that I certainly don't have. So after the year 8% they've received, their balance is £420. And the reverse percentage question is, what was the original? So we're in the past tense now. What was the original balance? So my sort of sneaky way of solving the sneaky problem of reverse percentage is to turn it into a normal percentage problem by invoking a little bit of algebra. So let's call the original balance B, okay? So let's call this B. And what I'm going to say is that if I knew B and I wanted to know the new amount in the account after 1 year, it would be very straightforward. I would just multiply that balance by the original value plus 8%. Now, I'm actually told what the answer to that is. I'm told that it's £420. And so you can see, therefore, that I just need to solve an algebra problem here. I need to solve the equation 1.08 lots of B is 420. In other words, the thing I don't know, the original balance, is 420 divided by 1.08. And again, steam-powered calculator to the rescue. 420 divided by 1.08 is 388 pounds and 89p. So this would have been the amount in the account, and we can just check this. I mean, it's a bit unnecessary, but let's imagine we had 388 pounds and 89p. We can calculate 8% of that by multiplying by 0.08. That's 31 pounds and 11p. And if we add that to 388.89, we get 420 pounds. So with reverse percentage problems, you can always just take your answer and check by applying the percentage in the forward direction. So one more example then. let's do a piece of biology here. Let's say that we have a bacterial infection of the kitchen or something like that. No, hopefully not of a person. So let's say we have some bacteria, and after application of the antibiotic, the bacterial population is just 5 trillion bacteria. Okay. And we're told that it has decreased by 50%. Or let's just make it a funny number, 57%. Okay. And we're asked to find out the original population. So let's call the original population P. Okay. And what we know is that that original population multiplied by 1, which is the original value, take away 57%, which is 0.57, is 5 lots of a trillion. So I'm just going to write 5, and we're going to deal in units of a trillion. So the original population size times 1 take away 57% is 5 trillion. And again, you'll see what I've got here is a algebra problem to solve. So 1 take away 0.57 is 0.43. That times P is 5 trillion. And so P will be that 5 trillion divided by 0.43. And if I work that out, 5 divided by 0.43 is 11.6. So the original population would have been 11.6 trillion. I'm just reintroducing the kind of the unit there of a trillion. So I don't know, I think sometimes students are taught some kind of rule. Oh, you just divide by this, or you just divide by that. But the problem with learning it as a rule is that it's so easy to forget and to make mistakes. I think it's better to go through an algorithm which shows clear understanding, which is what I've tried to illustrate here, which ultimately may end up with a little calculation, which is perhaps the rule that somebody learned. But by doing it through an algorithm, then there'll be no risk of error. You can just make each step forward using logic and understanding. And I've said this before, and it's so important in maths to think about doing maths as an exercise in clarity, in confidence, in logic. Maths is not a set of rules that are learned on an ad hoc basis and applied in an ad hoc way. That would be such a terrible way to experience maths. It would be like learning a long table of irregular verbs in some strange language. Maths is not like that. It's a structure where everything is connected and everything can be done in a clear fashion. And often there's more than one way of doing things too, which means that you can check to make sure that what you're doing is correct. Right, so that's percentages. I hope that's been helpful, and I'll now in the next tutorial be going on to talk about scientific notation and significant figures. Right, see you next time.